In this PowerPoint, we're going to look at the position versus time graphs and how that relates to a velocity versus time graph for constant motion. So what is speed and initial position in the equation for this graph right here? So we got this line that obviously has a positive slope, and we got a position versus time graph. So let's figure out the speed first. Now remember, the speed for a position versus time graph is going to be the slope. So we're going to take 2 points, and then we take the rise of a run of those 2 points. So the rise is going to go from 30 up to 50, which gives me a rise of 20, and then we go from 6 seconds to 18 seconds. So 18 minus 6 gives me 12 seconds. Now, these are 2 random points along the graph. You can pick any 2 points in the rise of a run. The slope is going to be constant. So we take the rise divided by the run. That means the 20 divided by 12, and that gives us 1.67. As you see here, no repetim bar. So this actually gives you 1.66666. So we don't want to do the 1.6 and then the repeating bar above it. The reason is because in physics, we actually have to take a measurement of that of the number, and if you have a repeating bar, that implies an infinite number of significant figures, which in math is okay, but in science that's impossible, and that doesn't make sense. So we don't use repeating bar. We always round to the correct number of significant figures. So the next question is, what's the initial position? So the initial position is going to be where the y-intercept is. So the initial position being the y-intercept, this one's going to be 20 meters. That's where it crosses the y-axis right there. And then the last part here is, what's the equation? Well, the equation is going to follow the y equals mx plus b, m being the slope and b being the y-intercept. Now, if we take the velocity, which is 1.67, and then the initial position, which is 20, we plug it into this equation, which is the final position, is going to be equal to velocity times time plus the initial position. Now, this follows the y equals mx plus b format, where m, the slope, is the velocity, and the b, the y-intercept, is going to be the initial position. So we plug those in, and we get our final position is going to be equal to 1.67 times time plus 20. Then we're going to solve for several points on this graph that we can't see on the graph. So basically extends beyond the 21 seconds that the graph has on here. So we're going to, at time equal to 80 seconds, what's going to be the final position? When the final position is 120 meters, what's going to be the time there? When the time is 40 seconds, what's the displacement? So it's a little bit different question. And then if the displacement is 90 meters, then what's the time there? All right, so let's deal with these two right here. At time equal to 80 seconds, we plug in 80 into the equation, 1.67 times 80 plus 20, we get 153.6. Now we use that same equation where we plug in the final position is going to be 120. Now we got to isolate our time, so we subtract 20 from both sides. That gives me 100 is going to be equal to 1.67 times time. We divide it by 1.67, and we get that the time is going to be equal to 59.9 seconds. Now to find the displacement, we got time equal 40 seconds. What is the displacement? Well, we got to rearrange this equation a little bit, because displacement is final position minus the initial position. So if we take this initial position to the other side, final position minus the initial position gives me displacement, and that leaves velocity times time over here. So we can use this equation where displacement is going to be equal to velocity times time, which actually the strict definition of velocity is displacement divided by time. So if we take that time that we divide to the other side and we multiply, then that gives us this equation. So we can plug in our velocity, which is going to be 1.67. Then we can use this equation in order to figure out the displacement. So we plug in 40, and that's going to give us 66.8 meters. Now, if we have a displacement of 90 meters, then we could take 1.67 to the other side. We divide both sides, and that gives us a time that's going to be equal to 53.9 seconds. All right, so here we have a position versus time graph, but we have several different velocities as it goes through. You can see that the slope is changing the entire time. So what we're going to do is we're going to split this into each section where we have a different motion, and then we're going to deal with each one separately. So let's talk about the first section here from 0 to 4 seconds. From 0 to 4 seconds, we see that there's no slope, which means there's no displacement. Remember, displacement is final position minus the initial position. Final position here at 4 seconds is 2 meters, and then initial position is 2 meters, so the total displacement is 0. And if displacement is 0, the velocity is 0. The last part here, what direction? Well, if it doesn't have a velocity, it doesn't have a direction. All right, so you can look at this graph and actually tell that there's no velocity because there's no slope. Remember, velocity is the slope of a position versus time graph. So the first section has 0 meters per second for its velocity. The second section, we find the displacement. It's going to be final position minus the initial. So final is 5, the initial is 2. 5 minus 2 gives me 3. Take that, divide it by time, so 3 over 6, because that's 10 seconds from 4 seconds, so that's a 6-second difference. And that's going to give me 0.5 meters per second for the velocity. And because it's a positive slope, then it's going to be the positive direction. Now, we don't really indicate what direction positive is. Positive could be to the right, positive could be up, but at this point, the only thing we know is that it is moving in the positive direction, whatever that is defined as. So our velocity is going to be positive 0.5 meters per second. This point right here, section 3, we're going to have from 10 to 15 seconds, we have 0 slope, which means we have 0 displacement, 0 velocity, and obviously with no direction. For section 4, we go from 15 to 19 seconds. We see that the final position here is 1 and the initial position is 5. So 1 minus 5, final minus initial, gives me negative 4. So finding the velocity, we take that negative 4 divided by time. So 19 minus 15 gives me 4. So negative 4 over 4 gives me negative 1. Now, because we have a negative slope, that means we're moving in the negative direction. So negative slope means negative direction. So our velocity here is going to be negative 1 meter per second. For section number 5, we have 0 slope again. So we have 0 displacement, 0 velocity, and no direction. And then for section 6, we end at 7 meters. We start at 1. So final minus initial is going to be 7 minus 1, which gives me 6 meters. Now the velocity is going to be displacement divided by time, so that's 6 meters divided by the time, so we go from 22 seconds to 30 seconds, so 30 minus 22 gives me 8, 6 divided by 8 gives me 0.75. So it's in the positive direction because it's a positive slope, so positive 0.75 meters per second is going to be my velocity. Now with all that, we need to figure out what the velocity versus time graph looks like. So that was the position versus time graph, but we can develop our velocity versus time graph based on that. So if you remember, we transitioned at 4 seconds, 10 seconds, 15 seconds, 19 seconds, 22, and 30. That's where we had the transitions between the different velocities. And if you remember the velocity, it was 0 meters per second, 0.5, 0, negative 1, 0, and then 0.75. So let's go ahead and graph these. From 0 to 4 seconds is going to be 0. From 4 to 10 seconds, it's going to go up to 0.5. And then from 10 to 15 was back to 0. And then from 15 to 19, it was negative 1. And then 19 to 22 is back to 0. And then from 22 to 30 seconds, it was 0.75. So this is what our velocity versus time graph looks like based purely on the position versus time graph. These little dashed lines, they don't have to be there, but what that does is that helps me know that there was a transition without having an empty space in between. This question says the graph to the right, actually the one at the bottom, are 2 people running. Describe the position of the runner A relative to runner B at the y-intercept. Well, at the y-intercept, you can see that runner A is actually ahead of runner B. It's runner A's position is greater than runner B. So runner B starts at the origin, runner A starts a little bit ahead. Now, the second part, part B, which runner is faster? The slope of the graph tells us the velocity, and even though we don't have any numbers here, we can see that runner B has a steeper slope, therefore runner B is faster than runner A. And then at point P, what happens? Well, at point P, they're at the same place at the same time. But you see before point P, runner A was ahead of runner B, but after point P, runner B is ahead. So what happens at point P? B passes runner A. B passes runner A. Next question says the figure to the right is a position time graph of a rabbit running away from a dog. So describe how the graph would be if the rabbit was twice as fast. Well, twice as fast means twice the velocity, which means the slope for position versus time graph is going to be twice as much. So again, position versus time graph, the slope equals the velocity. So with twice the velocity, you have twice the slope. Part B says describe how this graph would be different if the rabbit ran in the opposite direction. Well, the opposite direction, remember direction is indicated on a graph by the whether the slope is positive or negative. So a positive slope is the positive direction. The opposite direction, it would have a negative slope. So with a velocity indicating direction, the slope of the position versus time graph would be negative when it's going in the negative direction.